Hello students, so today we will be talking about buffers. So what is a buffer or a buffer solution? So it can be described as a solution that resists a change in its pH when either hydroxide ions or protons are added. It can also be described as a solution of a weak acid or a weak base and its salt. Here are some important facts about buffers or buffered solutions. First, they are prepared by combining in aqueous solution a weak acid and its conjugate base or a weak base and its conjugate acid. Second, they resist changes in their pH values even if a limited quantity of strong acid or strong base is added. And then, buffer solutions of molecular acids and their conjugates accomplish that stability of pH by shifting their equilibria to use up added hydronium ions or hydrogen ions, or to replace these hydronium ions or hydrogen ions that has reacted with the hydroxide ions. So a buffer solution must contain a relatively large concentration of acid to react with any hydroxide ions that are added to it. And it must also contain a similar concentration of base to react with any added hydrogen ions. Furthermore, the acid and the base components of the buffer must not consume each other in a neutralization reaction because it will cancel out the buffering capacity of the buffer solution. How to prepare a buffer solution? So we prepare a buffer solution by mixing comparable molar amounts or equal concentrations of the weak acid or weak base and its salt, or the conjugate acid or conjugate base. Let's say, for example, we mix a comparable amount of acetic acid and its salt, which is sodium acetate, to water. So the equilibrium concentrations of both the acid and the conjugate base are assumed to be the same as the starting concentrations. A solution containing these two substances has the ability to neutralize either added acid or added base. So we know that sodium acetate is a strong electrolyte, so therefore it is assumed to dissociate completely in water, as the equation shows. And if an acid is added, the hydrogen ions will be consumed by the conjugate base in the buffer, which is the acetate ion, according to the following equation. If a base is added to the buffer system, the hydroxide ions will be neutralized by the acid in the buffer, as shown by this equation. And in general, a buffer system can be represented as salt acid or conjugate base acid. Thus, the sodium acetate acetic acid buffer system that we have discussed can be written as follows. So it can be written this way. So we can have the sodium acetate acetic acid buffer system, or we can indicate the common ion, which is the acetate ion acetic acid buffer system. Either way, both are correct. So what is buffering capacity? Buffering capacity is the effectiveness of the buffer solution, and it depends on the amount of acid and conjugate base from which the buffer is made. The larger the amount, the greater the buffering capacity. Okay, let us have an exercise and apply what we have learned. Which of the following solutions can be classified as buffer systems? So we are given three solutions. We have the monopotassium phosphate, or the potassium dihydrogen phosphate and phosphoric acid. We have the sodium perchlorate and perchloric acid, and then pyridine and pyridine hydrochloride. Now, how are we going to find out which among these three are buffer systems? So first, what constitutes a buffer? What makes up a buffer? So we know from our previous discussion that a buffer consists of a weak acid or a weak base and its salt. So which of these three solutions contains either a weak acid or a weak base and its salt? So let us start with letter A. Phosphoric acid, or H3PO4, is a weak acid, and its conjugate base is H2PO4-, or the dihydrogen phosphate, which is a weak base. So therefore, letter A is a buffer. Now let us go to letter B. We are given sodium perchlorate and perchloric acid. Now, if you can still remember from the 7 strongest acids, perchloric acid is actually a strong acid, and its conjugate base, which is ClO4 minus, is an extremely weak base. So this means that the ClO4 ion, or the perchlorate ion, will not combine with a hydrogen ion in solution to form or to reform the strong acid perchloric acid. So thus, letter B cannot be a buffer system. Now, how about letter C? How about pyridine and pyridine hydrochloride? So pyridine is actually a weak base and its conjugate acid is a weak acid. So therefore, letter C is also a buffer system. And that is how we are going to determine buffer systems. How does a buffer work? Let's consider a buffer system composed of a weak acid, which is represented by Ha, and its salt, Ma, where the M ion or the M plus could either be sodium ion or potassium ion or any other cation ion that does not react with water. So the acid dissociation equilibrium in this buffered solution involves both the acid and its conjugate base. So this is the corresponding acid dissociation constant expression. And we see from this one, we can have for the concentration of hydrogen ion will be equivalent to Ka multiplied by the ratio of your weak acid and its conjugate base. So we see from this equation or from this expression that the concentration of hydrogen ion and therefore pH are determined by 2 factors. First, the value of Ka, or the acid dissociation constant for the weak acid component of the buffer, and the ratio of the concentrations of the conjugate acid-base pair, which is represented by the concentration of Ha over the concentration of its conjugate base, or A minus. Okay, now going back to the buffer system, if hydroxide ions are added to this buffered solution, they react with the buffer acid component to produce water and the conjugate base A minus. This neutralization reaction causes the concentration of the weak acid to decrease and in turn causes the concentration of the conjugate base to increase. So as long as the amounts of weak acid and the conjugate base in the buffer are large, relative to the amount of hydroxide ions added, the ratio between the weak acid and the conjugate base does not change much, and thus the change in pH is small. So if hydrogen ions are added, they now will react with the base component of the buffer. An example of a weak acid and conjugate base buffer is the hydrofluoric acid fluoride ion buffered solution. So this buffer solution contains equal concentrations of hydrofluoric acid and the fluoride ion. The addition of hydroxide ion reduces the concentration of the hydrofluoric acid and slightly increases the fluoride ion concentration. While on the other hand, the addition of hydrogen ions reduces the concentration of the fluoride ions and slightly increases the concentration of the hydrofluoric acid. So now you can see the effect of the addition of common ions in buffered solutions. So if the proton is added, the concentration of the weak acid slightly increases. Now, if the salt or the conjugate base is the one that is added, then the conjugate base concentration will now slightly increase. So it will depend on the type of common ion that will be added into the system of a buffered solution. Calculating the pH of a buffer. Because conjugate acid-base pairs share a common ion, we can use the same procedures to calculate the pH of a buffer that we used to treat the common ion effect in the previous video. So now we have here the formula or the equation for calculating the pH of a buffer. So the pH is equivalent to pKa minus log, and then the ratio between the weak acid and the conjugate base. Now, if we will be modifying that equation, then the pH of a buffer is equivalent to pKa plus log of the ratio of your conjugate base over your weak acid. Or we can simply write pH is equals to the pKa plus log ratio of your base over your acid. Hence, we call this equation as the Henderson-Hasselbalch equation. We will be discussing more of the calculations of the pH of a buffer on the next video.